Alright, let's use mathematical induction to prove something different. Let's prove 1 plus 2 plus 4 plus all the way up to 2 to the n, so the sum of consecutive powers of 2 is equal to 2 to the n plus 1 minus 1. So 1 plus 2 plus 4 plus 8 is 15. That's 2 to the 4th minus 1. So let's state this as a proposition. Let P of n be the proposition that the sum of consecutive powers of 2 up through and including 2 to the n is equal to 2 to the n plus 1 minus 1. That's our proposition. Let's prove it using mathematical induction. What do we need? First we need to prove a basis case. So P of 1 says 1 is equal to 2 to the 1 plus 1. This is 2 to the 0, 2 to the 1, 2 to the 2, and so on. So this is for n bigger than or equal to 0. So P of 0 says that the single term 2 to the 0, which is 1, is equal to 2 to the 0 plus 1 minus 1. Well, this is 2 to the 1 is 2, minus 1 is equal to 1. So if we just take the first power of 2, that's just 1, and that's equal to the next power of 2, 2 minus 1. So P of 0 is true. So I'm starting my induction now from 0 instead of 1. P of 0 is true. Now suppose P of n, where n is bigger than or equal to 0. So suppose that we've given some n, and we know that P of n is true for that value of n. Let's prove that P of n plus 1 is also true. Well, state what you know. We know that P of n is true, and P of n says 1 plus 2 plus all the way up to 2 to the n equals 2 to the n plus 1 minus 1. And now let's just do some algebra. I'm looking for something that says P of n plus 1 is true, and I know that P of n plus 1 is going to say that this plus an extra 2 to the n plus 1 equals 2 to the n plus 2 minus 1. So let's just add 2 to the n plus 1 to both sides, right? This is equal to this. I can add something to both sides and still have an equality. So 1 plus 2 plus 2 to the n plus 2 to the n plus 1 equals 2 to the n plus 1 minus 1 plus 2 to the n plus 1. All I've done is add this single term to both sides of this equality. So this is absolutely true. And this right-hand side, I've got 2 to the n plus 1 plus 2 to the n plus 1. That's 2 times 2 to the n plus 1. And I still have to subtract my 1. And 2 times 2 to the n plus 1 is 2 to the n plus 2 minus 1. Well, I've just proven that this is equal to this. And that's exactly what P of n plus 1 says. P of n plus 1 is the proposition that 1 plus 2 plus 4 plus 2 to the n plus 1 is equal to the n plus 1 plus 1, 2 to the n plus 2 minus 1. So starting with P of n, we've shown that P of n plus 1 is true. Well, if by assuming this we can show this, that means that P of n implies P of n plus 1. We've got P of 0, we've got P of n implies P of n plus 1, therefore P of n is true for all n bigger than or equal to 0, and the reason for that is mathematical induction. Very powerful technique. Lets us prove something relatively easy and conclude from that something that's generally very difficult to show directly. Because this is a statement that's true for all values of n. This we only have to show is true for this one value, and we're assuming it's true for this value also. So this is a generally easier thing to show, but we put that together with the base case and we get the general solution.